Yes, hello everyone. Good morning, good afternoon, good evening, depending on where you are. And welcome to UCGIS webinar, Tobler's First Law in GeoAI. I am Yongmei Lu. I'm with Texas State University, and I am your moderator for today's webinar. And our speaker today is Professor Wenwen Li. And Dr. Li is a professor in GI science in the School of Geographical Sciences and Urban Planning at Arizona State University. She directs the Cyber Infrastructure and Computational Intelligence Lab and serves as the research director for Spatial Analysis Research Center at Arizona State University. Her research interests include cyber infrastructure, big data, geospatial artificial intelligence, and their applications in data-intensive environmental and social sciences, including global warming and Arctic change, terrain analysis, disaster relief, and water insecurity in underserved communities. Her research has been supported by multiple funding agencies, having received a total of $14 million research grants as PI and co-PI. She is the recipient of the prestigious NSF Career Award and the inaugural Mid-Career Advancement Award from National Science Foundation. So we welcome Dr. Li today to give the talk. But before we move on, and I want to remind everyone that by default, you are muted. And please feel free to submit your question using the Q&A button at the bottom of your screen. Thank you. Now, Wenwen.
Thanks so much, Yongmei, for the very nice introduction. And I would also like to thank Dr. Lin Bian from University of Buffalo to nominate this topic to present at the UCGS webinar series. So today I'm going to introduce my recent publications in the Annals of AAG, along with some other research work discussing the integration of spatial principles and laws, especially the Tobler's first law in the growing field of GeoAI. I hope by now many of you have heard of this term GeoAI for several times. So in a nutshell, GeoAI is a combination of geography and AI. It includes applications of advanced AI methods for solving geospatial problems, and it also includes the integration of geospatial domain knowledge and the spatial principles to help the design of better AI models. So this is really a two-way communications here, with knowledge transfer from AI to geo and also from geo to AI. And this field evolves as its three-pillar technology evolves. First, the proliferation of geospatial big data, such as like large amount of remote sensing imagery and the output from numerical simulation models and the sensor observation data, which are being collected in near real time from the smart city infrastructure or other kind of environmental monitoring network. And we also have the social media data, which contains a lot of public opinions, and we can also leverage that for human mobility research. And these geospatial big data offers ample opportunity for us to ask new questions and make new discoveries. And the other two brother technologies, like to advance AI, is AI and computing. Because to allow us to design complex AI models and run it with big data to solve complex real-world problems, we need the advanced computing support to be able to do so. And my particular interest in GeoAI is its application in image and terrain analysis. So here I just want to quote Dr. Dang Wright's statement that she made earlier. She said, "The danger of climate change is with us. If we want to develop an approach to cope with climate change on a global scale, we really need to develop the capability to achieve continuous and near real-time mapping and monitoring of the Earth's surface, and developing strategies to scan large amount of satellite imageries, such, for example, the Planet, which is a commercial image company, they are collecting about 10 terabytes of data per day. And after these, their capacity improvement is done, they can collect the 40 terabytes of data per day. So, but our analytics capacity is behind the rate of data increase. So we really need to develop this advanced and intelligent analytical capabilities to understand and monitoring the change by detecting the natural features, also the man-made features on the Earth's surface. And the GeoAI can use to support applications of important societal benefits. So for instance, one of the application area that is very near and dear to my heart is to leverage GeoAI to support Arctic permafrost research. And for those of you who are not familiar with permafrost, they are frozen ground that can be like widely found in the Arctic region. And a lot of this infrastructure in the Arctic, like buildings, road network, oil pipeline, are all built upon this permafrost. So I'm showing some pictures about some typical permafrost features like pulsar, pingo, and ice wedge polygons. And many of them patterned ground. So their appearances and changes in terms of extent are very important indicators of Arctic warming and permafrost melting. So if we can identify the changes in terms of extent of these landforms, we can better predict to what degree the permafrost degradation is occurring. And also we can develop actions that can help us to better address and cope with the change in the Arctic. And the GeoAI can also use to support the search and rescue operations. So this is a story published in Washington Post, and it's about a hiker got lost in Mount Waterman areas near Los Angeles. So he was able to send this photo before his phone died to his friends. And the guy with a lot of experiences in remote sensing imageries was able to pinpoint the approximate location of where this person got lost to help the police officers to perform the rescue of this person. So GeoAI can really empower these efforts through automated scanning of remote sensing imagery, especially when the search is over a large extent and in a foreign region. And these two examples shows how we can leverage GeoAI to achieve intelligence and to achieve automation to help us to solve real world critical situations like these search and rescue issues. And what enables GeoAI to achieve this is the recent breakthrough in deep learning, or one of the very popular model is called the convolutional neural network. So what it does differently from traditional machine learning is, in traditional machine learning, the model cannot take the raw data as input. So what we need to do in order to perform the analysis is to perform a manual feature extraction to identify the important independent variables that would affect the outcome. And then we can apply a classification model like a random forest, or we can apply a regression model in order to identify the relationships between the input and the output. So again, in traditional machine learning, this process of feature extraction needs to be done manually. But deep learning has the ability to directly apply on the raw input, may it imagery or a text messages, and then perform the feature extraction to find the important image features automatically, and then send it to use that to support the machine either doing classification or other prediction tasks to achieve highly accurate prediction. And deep learning's application in image analysis can be categorized into three broad classes. Image recognition is the simplest one. So it only needs for us to predict what is inside of the image. So in this case, we will need to predict there is ship and also dog in this image. And then object detection goes one step further. Besides predicting what's inside, it also requires the model to predict the locations of each object by drawing the bounding box around it. And then instance segmentation goes one step further So it requires, in addition, to delineate the exact boundary of each object. But a lot of these segmentation tasks are actually based upon object detection. So once you have detected the location of the object, then by applying a mask, you will be able to delineate more accurate boundary of each object. And the work that I introduced today are mostly falling into the object detection part. And we have also been recently doing experiments in this realm, and hopefully I will have opportunities to share that with you in the future. And in terms of the natural feature detection, there are a lot of the challenges. So for instance, natural features tend to have only vague boundaries compared to a lot of these man-made features. This is due to the erosion and other type of land processes. And many of these features tend to have complex topographic and spatial structures. So here on the right, I give you an example of the Bachelor's Canyon in Montana. So without looking at these labels, for us who doesn't have a lot of these expertise in like landform, then it will be difficult for us to drawing and identifying the main body of the canyon. So this also tells us that preparing the training data to enable GeoAI to be learned from this ground truth is also challenging compared to for us to provide the labels for other man-made features like buildings and airplanes and other kind of objects. And a lot of these natural features tend to have high interclass similarity and also high intraclass heterogeneity. So for instance, two natural features that belong to different classes, they may look very similar to each other, so making the task difficult. And in a few slides, I will show you an example of this. And for traditional algorithm, especially related to terrain analysis, we normally will use DEM data because the DEM captures the elevation changes. But a lot of these traditional algorithms, they tend to work on and work better on this smoothed out data set, like the lower resolution data. When there are high resolution elevation data available, because a lot of these details like rocks or local spikes will be captured in the data. But the traditional algorithm is not robust enough in order to cope those kind of noise captured in the high resolution imageries. So that makes it challenging for an accurate detection of natural features. And in the deep learning space, like we know that a lot of these GeoAI applications are data hungry. So we need to feed the model with a lot of the ground truth data. So I have mentioned the one challenge of preparing the training data for natural feature detection because it really requires a lot of the expertise to create a high quality data set. So in the literature, there are, although there are increasing amount of training data available to support image analysis tasks with GeoAI, but in terms of natural feature detection, there are not so many of these data sets available right now. So to address this challenge, my team has developed a series of methods. Like any other interdisciplinary field, I argue that the advances of GeoAI need to go through 3 stages: application, integration, and cross-domain innovation. So application is the simplest one. So it involves applying an existing AI methods to solve a new problems. So we do not have to do a lot of these model modifications at the application phase, but instead we can explore whether they can be applicable to solve a problem in our domain. And then the integration will involve adapting the AI models so that we can foster the best practice in the geospatial problem solving. So this may require us to modify the AI architecture to better cope and deal with the data characteristics of the domain problems. And then the innovation is the most important part. To make the GeoAI to create long and lasting impact, we really need to also think about how to export geospatial knowledge and spatial principles to guide the design of better AI models so that we can not only solve geospatial problem better, we can also develop better AI models to better solve non-spatial problems. And then next, I will introduce how we approach this research in our work. So our first application is a simple creator detection problem. What we did is we collected these images by Google image search, and then performed the labels, and then send the data into a very popular object detection models called the FastR CNN. And here are the results. So the detection accuracy measured by mean average precision has reached up to 99%. So this MAP is actually a composited score between both precision and recall. So we can see the model has done very well in terms of this simple binary object detection task. And from the result, we also can see that both the larger objects and the smaller ones and the ones with overlapping boundaries can all be detected. So this work is the very first applications and help us to climb up the learning curve of GeoAI. But what is missing here? We collected this data from Google image search. So there's no location information associated with the data. So what is missing is the geographical frame that allow us to stack multi-layers of geographic information over the same region so that we can gain a more comprehensive view about the study area. So this is also what makes geospatial data so special. And in fact, multi-source data is also very helpful to support the terrain analysis. So let me show you an example here. So here are the two lakes. One is a crater lake and one is a mono lake. One located in Oregon and the other is located in California. So they too were actually existed in two very different types of basins. But from remote sensing image alone, they look very similar in terms of their appearances and shapes. But if we take a look at the DEM data and its derived parameters, we can certainly see the distinctive patterns between these two kind of features. So this example shows that it's really important to consider multi-source data to make the GeoAI model more powerful in doing natural feature detection. And so although the multi-source data fusion has been a common practice in the remote sensing community, but in a deep learning framework, considering multi-source data has only been recently studied. And one common treatment is once we have a new data piece or new data source, what we can do is we can send each of them to an individual feature extraction pipeline. So as we know, a CNN model would help us to achieve this goal. And then after the feature extraction is done, we can fuse the data here and then send the fuse data to the next stage of the processing. But this way of dealing with multi-source data has two challenges. So one is once a new data set is added, we add a individual feature detection pipeline. So this will dramatically increase the parameter space because we all know that CNN was able to extract important image features because of it is built upon a very deep architecture, which contains some contains millions of parameters for us to learn. So in this case, if we have multiple branches, then it will substantially increase the parameter space and making the model difficult to train and also difficult to converge. And another challenge is in this case, so it's a DEM and these two are all derived parameters from DEM. So although they provide important information about the terrain, but each only provide a partial information. So my argument here is the whole is more than the sum of its parts. So then it really makes sense to fuse this data to create a much enriched view about the terrain once the data is coming from the same source. This is a traditional approach of leveraging multi-branches is called a feature level fusion. And in our approach instead, what we did is when we have multi-source data And if they are from different route, like remote sensing and DEM, and each will go through their own data processing pipeline. But if all of this data coming from the same source, we instead will doing a data fusion through a blending technology to create a new enriched data set that fuse the information from all of this data set together. And then this new enriched data set will send to its own feature extraction pipeline. And then after the feature extraction is done, they are fused here and then send it to the next stage of the GeoAI pipeline. And this approach is called combined data level fusion and also feature level fusion. And we have conducted experiments to test and evaluate the performance of the model. So this figure shows as the model is being trained, what is the prediction accuracy of the model? So we can see that our approach, which is the blue line, has received a significant increase in prediction accuracy than the model leveraging single source learning using remote sensing image alone. And our approach is also works better than other multi-source learning approach leveraging purely the feature level fusion, which is the orange line. And in terms of the training speed, so it is not surprising that the model leveraging a single source learning, which only has a single feature extraction pipeline, which runs the fastest. Our methods runs at the speed of 2/3 of the speed than single source learning. But as we see from previous slides, it has achieved a much higher accuracy than this approach. And this multi-branch approach is the slowest, and it is about half of the speed from our methods. So this experiment shows that when we are leveraging multi-source data, it will really help us to improve both the prediction accuracy and also ensure that the training efficiency. And let's take a closer look at the data set. So we have developed this multi-source data set and also make it openly available to the general public. So if you take a look at this paper, the GitHub link of this data set can be found from the PDF file. And in this data set, we call it a GeoImageNet. So it is a multi-source training data set for GeoAI applications. And in this data set, it contains about 6 different feature types: basin, ridge, valley, bay, lake, and island. And for each of these features, we provide a pair of images. One is a remote sensing imagery, and the other is the enriched DM. So it is a fused result from multiple elevation products. And if we take a look at the prediction accuracy for individual feature type, and we know that bay, ridge, and valley, they exist in hilly terrains. So DM will work well for their extraction. So then we can see that after adding the DM as an additional source, we can see a substantial increase in the prediction accuracy for these 3 types of features. But what is interesting is bay, lake, and islands, they exist in more flatter terrains. But after adding DM, we can still observe an increase in prediction accuracy. So overall, it's all the detection accuracy have all been increased. So this experiment really shows us the added value of multi-source data in doing the image analysis and the land surface categorization. However, GeoAI still faces a lot of challenges. As I mentioned before, like any other supervised machine learning, we really need to feed the model with a lot of the ground truth data so they can learn continuously, gain intelligence, and also make good predictions. But the data preparation time is also is always very costly. So for instance, in an image recognition task, like we just need to predict what's inside, the cost for annotating a single object class will take about 2 seconds. But object detection task needs to, in addition, provide the bounding box annotation. And the average cost for that is about 35 seconds per image. So this combining these two tasks is what takes to prepare a training image for object detection task. So we can see that it's very time consuming. But the good news is that if we only provide a label for total object count information, it will only take about 1 second per image. So for instance, for this one, if we only need the annotators to provide 4, which is a total number of objects, it will take just 0.9 seconds to finish it, because our human eyes are so good at doing counting. So this motivates us to think whether we can achieve object detection by taking less information. So, and then we can make a good prediction still. So then if we can do that, the input of the model will be a total object count, which is 4 in this case. And then the output will still be the object location by drawing the bounding box around each object. So basically, we are trying to enable a strategy of learning from counting. And this is also a way of a weakly supervised object detection. We hope that by taking less information as input for the model, but the model will be smart enough to predict more information for us. So this is actually a more like a requirement for the model. So next I will introduce how we develop a new solution of AI that enables both better geospatial analysis and also better AI. So we generated this idea of learning from counting actually from reviewing the literature. So what caught our attention is this model called LSTM, the long short-term memory neural network. So it is a very popular model used for classifying sequential data, for sequential data classification. For instance, it can be used to recognize the phonemes in a speech audio for speech recognition. So giving a speech audio clip which contains sound, if we can provide the per frame labels, then LSTM will be able to predict each of these phonemes within this video clip. And it has 2 advantages. So one is, besides, it has the ability to capture the temporal dependence of a very of near neighbors. So that forms a short memory for LSTM. But it can only also it can also capture the temporal dependency over long time ranges, forming the long-term memory. Because of this ability, it can capture the patterns of the time sequence very well. And another advantage is that when this model is in combined use with a new objective function called CTC, connection list temporal classification, we actually don't need to provide the per frame labels. So for the entire video clip, we only need to provide one single label called sound. And then through optimization strategy, this model will be able to find the segmented location for each of these letters in the word. For instance, in this sound, in this this speech recognition, this model will be able to find 5 segmented locations separating each of these letters. So this is actually a strategy of a weakly supervised learning. So now our question has become, if we want to utilize this kind of a temporal data classification under the form of weakly supervised learning, how can we convert this 2D object detection problem, which is spatial, to a 1D sequential data classification problem, which becomes temporal? So luckily, the Tobler's first law of geography has provided us the guidance. And I think every one of us is familiar with the law, but essentially it gives us the, it tells us the essence of spatial information of being spatially dependent. So leveraging this Tobler first law, we'll be able to perform a serialization on the 2D images to create a 1D data after the serialization along the row directions and also along the column directions. So as we can see, this 2D spatial objects along the scan order direction, the spatial continuity is retained, but it also broken into multiple pieces along the direction, perpendicular the direction to the scan order, the scanning direction. But please remember the LSTM, it has the ability to capture the temporal dependence in a 1D sequence data. So what we can consider is each of these 2D objects, after serialization, it will form a unique temporal rhythm so that we can apply this data to the 1D, to the LSTM and the CTC model so that it can find the segmented location for these 2 objects. And through our observation, we found that the segmented location actually falls on or near each of these objects. So after we get the segmented location for each of these objects, then we can draw several candidate bounding boxes around these points and then send these candidate bounding boxes to the next stage of processing, like classification and also object detection. So this is how we convert, like start with a count information to get the approximate location for each of these objects, and then drawing some high quality bounding boxes around each of these objects for a better object detection task. Because prior to our approach, when we are doing this object detection in a weekly supervision manner, because this bounding boxes information is not provided to the model. So a lot of the model has to drawing like a very large number of candidate bounding boxes, like some up to 2,000 of different shapes, different size to exhaust any potential locations of where an object may occur in this image. But through our approach, we can relatively accurately identify where the object is. And then in our approach, we only need to generate about 100 and most 200 of these bounding boxes. So making the processing more accurate and also efficient. So to evaluate our model, we have prepared a number of data sets. So the first data set is a Mars creator data set. So we are leveraging our approach for the creator detection on Mars. This is a simple data set because on Mars surface, there are not many different type of features, and also there's no vegetation on the surface. So we want to test out whether our methods work. So what we did is we compare our model with a few other very popular to cutting edge models in weekly supervised learning in the computer vision field. So WSDDN is a phenomenal work in weekly supervised object detection. And then OICR is a refinement version of WSDDN through multi-stage refinement. And then CMIDN was a cutting edge model at the time when we conducted the experiments. So from the detection accuracy, we can see that our model has received about 10% of increase in terms of detection accuracy than the cutting edge model in computer vision. And the runtime wise, our model is not the fastest, but it still runs faster than the other cutting edge model. So, but let's remember that it is always a trade-off between accuracy and also efficiency. And if we take a look at the result, so the red boxes are the ground truths, and the dashed blue lines are the predicted bounding box. So we can see, oh, this, by the way, the red boxes, which is the ground truth, is not provided to the model. So it is only used for evaluation. So we can tell that even without this information to be trained in the model can still make a relatively good prediction result. And in this image, we can see the contrast between foreground and the background is relatively low, but our model is still be able to predict like an accurate bounding boxes. And then for this one, we can see in the lower right corner, because the database that we use for labeling Mars creator only contains the labels for creators that is larger than 1 km in its radius. So a lot of the smaller creators were not annotated, but our methods can still be able to detect this. So this gives us the confidence that our model can actually achieve automation and high accuracy detection for generating a large global Mars crater database automatically. And we have also tested our model on an Earth dataset. So this is a dataset that contains 4 different features: hill, volcano, sand dunes, and craters. Again, the red boxes are ground truth bounding box, and the blue boxes are the predicted bounding box. So we can see our model again does pretty well in terms of predicting the locations and also the classes for the natural features. So we further conduct more evaluation, because if we want to prove that our method was state-of-the-art, can achieve state-of-the-art performance, we also needed to compare with other computer vision models and also using popular benchmark dataset in the computer vision field. So here we tested our model further on the Pascal VOC 2007 dataset, which contains nearly 10,000 images and about 24,000 of annotated objects of 20 classes, like persons, animals, and airplanes and vehicles. So we can see this data set is very different from what we have been tested in the geospatial field. And we compared our model with several other models in the computer vision field, including at the time cutting edge model CMIDN. And we can see under 2 different scenarios, the prediction accuracy of our model has been the highest among all the different models that we have compared. And these are the individual detection accuracy for each of these classes in the data set. So through this few works, I have shown a pathway of how we advance the GeoAI research in image analysis and natural feature detection. And it starts with a very simple application of AI, of using single source data for binary crater detection. And then we extended this work to multi-source, multi-type object detection, and eventually develop a novel GeoAI model that can achieve the weakly supervised object detection, which we can alleviate the burden of preparing training data set. And developing this GeoAI capability is really crucial for us to automating the mapping of the Earth's environment. However, there are still many challenges in terms of GeoAI and supervised machine learning work. So that's why it makes this field so interesting. So for instance, during the data preparation, like the training data preparation process, we really need to consider several issues. So first is the data diversity, whether our training data can reflect the actual population of the data. And this distribution actually shows the feature distribution in our GeoImageNet data set. So we can see they have quite distinctive distribution patterns. A lot of these lakes are near the Great Lake region and also near the coast, while these mountains are also clusters along some of the main mountain regions within the US. And also geographical representativeness is also an important consideration, because we are dealing geospatial data and they all have location information in it. And the scale is another challenge, because in dealing with natural feature specifically, we have very large features that extend like several hundred miles, like mountain ranges. And we also have smaller objects like craters, which may only range within 1 to 2 kilometers. And another thing is, if we want to incorporate multi-source data, then we will need to align this data. So because this data may have different projections and different resolutions, so a lot of the pre-processing is needed to ensure that the data aligns very well to each other. And another challenge is the location sensitivity. So during the preparation of the training data, we cannot always make the feature to stay near the center of the image, because the GeoAI models has memory. If our feature are always located near the center of the image, then the model may always want to predict something in the center, even though they may or may not be of our interest. And another challenge that we have widely discussed is, if we want to make GeoAI to create long and lasting impact, we really need to better think of how we can justify the scientific contribution of GeoAI. So one of the ways that, and we also have been seeing a lot of the increasing work, is towards a methodological innovation that can allow us to incorporate spatial principles and the unique characteristic of spatial data and the spatial processes to supervise the learning process. And in the future, I think we'll be doing work in three distinctive areas, or interconnected areas. One is a better models. So we have discussed whether we can develop a more even smarter models that can conduct a self-supervised learning, so that we can relying less on the training data set. And another thing, as I mentioned, because a lot of the GeoAI models deal with geospatial data, and how we can enable the location-aware GeoAI, because a lot of this data, as I shown in the distribution patterns of the features in GeoImageNet, they have unique distribution patterns. And we are now doing experiments about how we can incorporate this distribution pattern into the GeoAI model to make it more powerful. And another area that I have been working on is to leverage GeoAI model to perform better science. So how can we leverage GeoAI to better answer pressing scientific questions in the earth and also social science domains? And another thing is about better training. If we want to continue advanced GeoAI, we really have to train our next generation students to help them to gain these advanced skills. But GeoAI, I think, still is largely missing in a lot of this curriculum across Earth and the geospatial domains. So one of our recent efforts is to receive a new NSF project doing cyber training. So we really hope to develop a series of training activities, both formal and informal, to help Arctic scientists and also geospatial scientists to gain the advanced AI-driven analytical skills. And one major activity that we will be launching, and this is actually what we're hosting this year, is a GeoAI challenge. And this year it is still open, and the focus is on GeoAI Martian challenge. So if you are interested, our deadline is December 15th of this year. So you are very welcome to join us. We have provided a data set, and we have also provided a sample code for you to start with, and also develop a novel AI model so that we can advance this field forward together. And in the future, we'll continue host this event. So if you would like to collaborate with us, please ping me, and we will do this as an important cyber training activities. And before I end, I would really like to thank two GIS giants who has made significant contribution in this field, but unfortunately we lost them this year. So one is Professor Stan Openshaw. I didn't have opportunity to interact with him, but his book in artificial intelligence in geography 20 years ago really opened up the field and allow us, many of the younger generations, to be able to continue exploring and hopefully contributing to the field. And I would also like personally to thank Dr. Lin Ursary, because a lot of this research I have been talking about has been inspired by Lin. And Lin was also leading a lot of these GeoAI efforts at USGS for topographic mapping. And he was also a long-term member in UCGS. He had served as the director on board, the chair of the research committee, and he was also the UCGS president in 2004. So I hope that we will be able to carry their spirit and continue contributing and advancing this field. And that concludes my talk. So thanks so much, and I welcome your questions.
Thank you, Wenwen. Wonderful, wonderful talk. And we do have a great audience here. We have 80 plus people here and listening. And I just want to, there are some questions, but I also want to quickly follow up on Wenwen's slides about the big giants in GI science who actually, the whole community, our whole discipline community is built on the shoulders of big giants. So especially for UCGS this year, we lost quite a few. Lin Yusuri is one, and Duan Mabo, and Art Gattis, and this past Saturday, David Mark. These were UCGS fellows. So it's a big loss to our community. All that, this is about this webinar. So we do have a few questions. So if Wenwen, you don't mind, I'm going to read some of the questions from the Q&R boxes here. Yes, so first one, yeah. First one, for your integration pipeline, have you considered progressive fusion, a fusion approach that allows multi-model data to fuse not at the beginning, feature level, nor decision level, but in a progressive manner throughout the pipeline?
This is a very interesting question, but I'm not sure whether I completely understand what does a progressive
fusion. Yeah.
Yes. So there are several stages that we can make this fusion possible, right? As you mentioned, at the data level, we process the data at the input level to fuse them. And then at the feature level is after extracting these important image features. Yes, or at the decision level, that's a very last decision module in this pipeline. So could you give me a little bit hint about progressive mean? So you mean after training for
the question it says it is a fusion approach that allows multi-model data to fuse not at the beginning or feature level or decision level, but in a progressive manner throughout the pipeline.
Mm-hmm. So I'm still trying to understand.
That's we have other questions. I think that's they can email you, contact you if they want to clarify. All right, let's move on. The next one. When you say you use a prefused DEM product, do you mean an one-channel enhanced DEM based on several DEM products?
Oh, so this is, regular input of an image is RGB, right? So it's 3 channels. And then DEM data for this kind of numerical data, it only have 1 channel. So an easy way, without doing any fusion or blending, is if we have 3 channels, we can add the DEM as 1 channel and slope as another channel, aspect as a 3rd channel to put into it. But we didn't do that. What we did is we perform a blending technology to create a pseudo color DEM, because the CNN models does so well in terms of extracting features from optical images. So we want this DEM to reflect, to become more like an optical image so that its feature can be better extracted. Because we did some experiments to directly apply on this numerical data, but the patterns in the numerical data, they can they present is very different from the optical image, which is more suitable for the CNN model to extract to conduct the feature extraction. So again, we didn't use like a single channel enhanced DEM. Instead, we blend all of these features to generate a pseudo color DEM, pseudo color enhanced DEM. So it's kind of a color image as an end product.
Thank you, Wenwen. Next one is about the training data. For the computer vision benchmark test, what training data did you provide to your model to extract the 20 desired object classes?
Oh, for this one, we use all of their data set. So, but we didn't provide the bounding box label to our model because we want to enable the weekly supervised learning. So all of the data from Pascal VOC 2007 is entered into our model for testing. So all the 20 classes, the data will be there because we needed to conduct a fair comparison with other computer vision models.
Thank you. The next one I think is related to sort of application. Great work. Have you tried your model on vegetation classification? What kind of challenges did you see or foresee in that context?
Thanks, Gagi. I haven't been applied to the vegetation classification yet, but we can certainly try. So gradually, what we have been doing in my team is to make all of our models and the data set available on GitHub. So anyone who's interested could download this data and the models to test out in different application scenario. So we really hope that our work can also benefit others. So in terms of the challenge, I think the resolution may be a challenge. If you can get a, because vegetation is relatively small, and if you get a lower resolution image, like a Landsat, the result may not be as good. So right now we have access to like half-meter commercial imageries, which give us pretty good accuracy in terms of small feature detection. But you can also conduct some upsamplings, pre-processing of the imageries to improve the detection accuracy.
Thank you. The next question is sort of along the same line. Did you attempt to discriminate natural landforms from artificial ones? For example, mining excavations, landfills, etc. I guess this is a difference between natural objects and man-made features, like mining, landfills.
Yes, so I haven't done like a lot of the testing on this mining field and landfills, but to compare with other kind of artificial features, like buildings and airplanes, airport. So a big difference is the size, right? A big difference is like I already showed in my slide. So natural features tend to have vague boundaries compared to man-made features, and their size may, like their extent may vary a lot. So how can we handle small object detection where there exists like a lot of the large numbers? And landform features and artificial features, they may all have demonstrated distinctive geographical patterns, like buildings in Europe and building in Asia. They may have different styles. Can we leverage those information to make the prediction even more accurate? So those are, I think, the interesting questions to answer. But I haven't tried to discriminate natural landforms from the artificial ones yet. So a lot of my focus has been natural feature detection, but this is a great suggestion.
All right, one more. This is also a little bit specific as well. Shaded relief is dependent on chosen solar angle. Do you attempt to match that up with no angle of the sun in RS images when developing that input for your model?
I think this is a very interesting. So actually what we did is in determining that parameter, we tried several different parameters and find one that visually can give us the most obvious patterns. But we didn't try like a changing angles and generate this shaded relief and to see how that affects the output. But it will be an interesting experiment. It also falls in the experiment called ablation studies. So thanks for the suggestion.
Thank you. I guess there's also, I got a not so technical question, but a general, very interesting question here. Deep learning methods are criticized as being less explainable than traditional methods. how did your research address this issue?
Okay.
Versus deep learning versus traditional methods.
Yeah, I think this is a very, very great question, and it's very difficult to answer. So if we want the model to have really good prediction accuracy, and deep learning certainly has shown its outstanding performance in this realm. But we also are doing some tests that we are integrating some of the known patterns of spatial processes, and then we can see the improvement, and that will help us to improve the explanation of what the model is doing. So besides the CNN, we are also adding different, we call it geo priors, or the multi-branches. So those branches coming from known spatial processes. So we can better explain, after adding this new information, how would the model be better at doing the detection? So this is some of the controlled experiments to help us improve the understanding of how the model does. But we also found that it sometimes only works in geospatial realm. When we are testing our approach in another different data set, then we didn't see that significant improvement. Instead, if we use a deep learning based prior or the additional branch, it does show improvement, a lot of the improvement in the result. So it is a balance, right, between explainability and also the prediction accuracy. Sometimes deep learning may extract some very complex patterns that we as humans even are very difficult to understand, but it works. But again, then this will make it very difficult to explain. So it's really, we need to decide how scientific trustworthiness of the model that we want it to produce. But we should, I think, develop further efforts to make this two branch converge between explainability and high detection accuracy.
Thank you so much, Wenwen. Considering time, I think we should wrap this up, but there are certainly more questions. I would like to encourage our audience to please, Wenwen has her email address here on the screen, so please feel free. I'm sure she will be happy to continue the discussion with you through emails and other, future opportunities. Probably we see each other. Thank you, and this wrap up our webinar, UCGS webinar, Tobler's first law of geography for GeoAI, and the recording will be available, I'm sure, in the near future for people from a membership institution. So thank you, everyone. Bye-bye now. Enjoying the rest of your day.
Thanks, Yongmei. Thanks, everyone.
Bye.